stop transcripting. Okay, so it is recording now. So Ravi, you can go ahead and let us start this tutorial actually.
Okay, okay, sir. Thank you. Okay, so I have been already introduced by Professor, but this is my roll number, and people can reach out to me whenever they have some issues regarding TCAD. So this is the roll number and followed by the iitb.ac.in uh, email address. So let me start on the TCAD. So this presentation consists of mainly three part. What exactly is TCAD, and how it is set up, how you can use, and while using it, can you check your things, whatever you're simulating, whatever you are doing, can you check it, and how good it looks like versus the textbook that you have read. And then there are some result I've compiled here just to show you that okay, whatever you have seen in textbook is actually done very well in TCAD as well. So there are parts where I'll be telling how to use TCAD, and then I'll be showing some results what I have compiled already. So the goal of this whole TCAD, using TCAD technology tool is to actually see. So can you see my cursor?
Yeah, we can see it, but you
Okay.
can put it in the in the laser form.
Okay. Okay. 1 second. Yeah. So I think this is better, right? Yeah.
Right.
Okay. So left side you have few pictures from textbook, and this is the mass capacitor. This side is metal, between is the oxide, which is the interlayer, and this side is you have silicon. And this is a typical band diagram you must be seeing, or you must have seen already in the textbook. And this is the picture that you see in the textbook of a MOSFET, a regular MOSFET having some source drain, a piece of straight gate contact, source contact, and drain contact. And this is a typical picture of drain current characteristics versus VG you see in the textbook. So the goal is to see all these things using TCAD, and how will we do it is just that we get the device first, we make the device, and we can make the device in 2D and 3D both. So the example that I'm showing is the 3D device here. So you see these diamond kind of a thing. This is actually the source drain. Middle part you see is the channel. So this is actually the advanced transistor design, which is called FinFET. And the below the picture that you see is actually the simulation result from a transistor. So you must have seen, if you haven't, that's not a problem, I will show you how it can be done. But just to remind you that this is just a band diagram. If I just take my cut axis from this point to this point, and we have a n plus, and then we have inverted channel, and then we have n plus. So this is a typical band diagram showing the effect of voltage. If we apply some at drain, how does the band diagram changes? So whatever you have seen at different instances about the accumulation, about the inversion, you can actually simulate everything, and you can see all the band diagrams, all the current densities inside the channel, in the source drain, and the output characteristics. So this is the overall goal of this TCAD. Okay, so let me give you a brief about how we can simulate a MOSFET in TCAD. So first thing is get a device. It's like we have the structure. So how can we make structure in TCAD? And that is using S process. There is so S process is anything which starts with S. It's actually called Centaurus, and the process is just the process. So it says S visual. That means Centaurus visual. So how can we get a device using S process? S process is a tool inside the whole TCAD setup. And so assume that we have a device now. Can we see the device? Yeah, you can see the device. And the tool for to visualize the device is an S visual. Now, since we have the device, can we see the fields inside the generator device? And can we see the doping concentration? Where are the junction formed? We can all see using S visual. Now, since we have a device, can we apply the voltage and check the characteristics? Yeah, you can always see. And that part is done in the tool called S device. So you can, whatever you have generated at the first place using S process, you can apply some voltage using S device, and you can get the IVs and the voltages, the the effect of band diagram, the effect of drain on voltage on the band diagram, you can all see. So yeah, that is done. But how does the Centaurus knows everything about the silicon material? I'm talking about when you simply do a calculation, you put Vg of 1.1 electron volt for silicon, and you set the permittivity of silicon of 11.2 or 12. So you provide the number, but inside TCAD, where are all these stored? So these all properties of the material that you use during your device generation and then characterize it, these all parameters, the values are stored in the parameter file, which is the part of S device. So S device has several parts. I will show you how exactly it is set up. And then yeah, of course, so if you want to see something different than the regular scenario, that means if you want to check some physics, include that physics command in the S device and check its impact. So it's like just choosing a model, so when I say model, it's just the mathematical equation implemented behind the TCAD for a simulation that can run in 2D and 3D. So in summary, you can use S process to generate a device. You can use S device to characterize a device. You can use S visual to see everything that you have done here and after or in between as well. So these are the main important tools in TCAD. So this is just a summary of all the tools, not all the tools, but the most important tools that you will be using. So as I already said, that the process, you can generate device structures like MOSFET and FinFETs in 2D and 3D mode. The device, you can actually characterize your device, whatever you have generated here, like an IV and CV and optical characterization, you can always do. Visualization of anything in between or after it can be done using S visual. And this is the tool that organizes everything, the process, the device, and S visual in a manner that you want to create a device, and then you visualize it. Then you check your IV characteristics, you visualize it. So this is just an organizer that can organize all your experiment based upon the choice of experiment to do. Okay, so now we know two things, that we can generate a device and we can characterize it. And the tools for those are S process and S device respectively. So this is just how the file system has been done and getting transferred to S device so that it can do a characterization. So if I just tell you that, okay, what exactly is this process? It is just a tool that takes an input as in a command file like sprocess underscore fps.cmd. So command file always end with extension of .cmd, and in the input of this particular S process, you will have structure, the command for the structure, and then you will have log files of the simulation, like whatever you have given to the command, is it exactly happening? So you can check your log file. If there is an error, you can check in the error file what is the error. If you have the bit higher temperature rate and it cannot extend into source drain, things like that, you can always check in the error file if the simulation fails. Now, whatever you have generated here, that should be the device. So if I say a device, that's actually a file that has all the information of grid points, doping, internal potentials, junction profiles. Everything is stored in this fps.tdr, and this is the file you will actually use to visualize how your device looks like. I will show you in the live session right after it how you can actually check your device. And then this particular fps.tdr, you provide it provide to S device, which is going to characterize it by applying the terminal voltage at gate, source, and drain, and substrate. Now, if you apply the voltage, how the S device knows that what are the physics that we are going to simulate. So those all physics, the model that you want to simulate, basically the physics that has some equation tested and tried and verified throughout the research of last like 50-60 years of whole device physics, you can put here whatever is available, you can put here, and you can provide the parameter for all the materials that has been used to generate the device, so that the tool knows all the information that you have in the S process, and then you combine it as an input section for the S device, and then you apply some voltage that can be given in the command file, and then you will have some output files. Based upon what you simulate, assume that we are simulating an IV characteristics, you will have a IV plot file in terms of XY data, and then you will have a device file that actually looks like a input file, but exactly differ in the terms of applied voltage, and the status is you can save anytime during the simulation. And then you will have an output file, which is the log file, where you can see the transients has been done, the ramp of the drain voltage is going on. You can all see in the output file. I will show you what exactly all these are, just giving you a brief idea. So I'll start with S process, and what you can do and how the things are set up in S process. I'll just quickly show, and then I will show the live session. So, hello, anybody asking something? Okay. So as we already know that the device generation is a step-by-step process, and you cannot just shuffle the process. You cannot shuffle the steps. So it has to be sequential. So we already know that you have to select a wafer, you define its resistivity like we do in the real fabrication. The almost similar steps has been followed. There are a few tweaks to it, and it's just an implementation limit that we can. That's why we have done it. But it's just that you select a wafer, define its resistivity, define the doping, define wafer orientation, and these all definitions are done in the S process command file. I will show you few sections of command file in this presentation. Then you define your P and N wells. Then you define your VT implants by implanting some dopant based upon NNP, and define your halo implant for the transistor. And then you activate the dopant. So basically, you already know that when we implant, we have to shake the device, shake the wafer with the temperature. So that's where you actually activate the dopant by providing it a temperature. And then you define the gate oxide by depositing by deposition methods. You want to etch something to make a pattern that looks like a transistor. You can use etching commands, and then you have to define meshing. So meshing is actually a new term in this case, because it's a simulation. It's just a space in 2 dimension or 3 dimension. So we need to define a meshing. So basically the points where all the semiconductor equation that you have studied will be solved based upon the models you choose, based upon the equations you choose, and this will all be solved on these mesh points. So I will show you what exactly the meaning of mesh points and how you should be very, very careful about the meshing. And of course, you should provide some contact so that you can apply the voltage at the terminals, and then you can check your IV and CV in the S device. So this is the brief what we can do and what are the options available in the S process. So if I just tell you, yeah.
Ravi, can you hold back to the Nick? So let us ask if anyone has a questions over here actually.
Yeah.
Okay, if there is no question, we can go ahead.
So in S process, do we need to remember all these steps, or the software will help us?
So yeah, so in the software you already have some library where example projects are already there. So you can pick one example project and learn how these things are processing step by step. It is already there.
Okay, Arnab, so to answer your question in depth, for example, like a meshing. So meshing is like it's like a small, like let's say you have a large square area. So you just wanted to have a small square divided into the several square. So there, so that you can solve your mathematical equations within these small square boxes. So if your machine is very small, so that your accuracy of this system or your calculation is more proper or more accurate. So depending on your requirement, or if you have a little larger, so or very large, then the accuracy of your like calculations will be little bit faint. So depending on your accuracy, like how much accurate results you need, so you can do your machining or meshing of your basically system. So it's completely depends on what you want actually. And also this etching is, you know, this normal etching process. We normally go to the clean room then we actually etch that source and drain. So that is what you do in the using these chemicals like hydrochloric acids, HF, or you have sometimes with hydrochloric acid or sulfuric acid. So here actually you can do with the software in the software level. So you can actually etch how much you want to etch actually by just clicking the mouse.
Yes,
So
yes.
all these steps is in your hand. It is like we are doing experiments. We are doing the same experiment what we used to do in the experimentally. We'll be doing over here. So these are the all parameters control what you have in your hand, so that you can control them and you can have the results what you want or what is your goal to achieve actually. So this is what all these control. These are actually all control which is there in your hand. So of course, if you go to the real application or the real device fabrication, so everything is not in your control. So the theoretically we will have this control, all this control we are in our hand, so that you can actually design the device whatever you want. Is it okay?
Yes, sir.
Okay,
Thank you
we
for
will see that when he will
yeah.
start the demo, like a live demo with the software.
Yeah.
Then we can change the machine, we can change the meshing, we can change the etching, and we can change the deposition step. So all these things we can change and see that how it is behaving. He will show
Yeah.
you maybe in
Yeah.
future.
Yeah. I will show you, sir. I will show everyone.
Please go ahead. Yeah.
Yeah. Thank you, sir. So as Professor explained that whatever these steps are is actually the controls, and it is whatever we do in the lab is actually control parameters here, and we can use these to modify and test our device based upon the requirement or the equipment we are designing. So right now I'm showing you the typical commands that I said. Okay, you can select the wafer, you can etch the things. So I'm just giving you a simple idea how the command file looks like when you are doing the steps when you create a device. So as I said that selecting a wafer in the command file. So basically you have a command file, you try to select a wafer. So it's a very simple command, let's say in it. I'm not saying that it's simple. It's just that it is the words are very much similar to what we have in a common language. So let's say init silicon bed, that means initializing silicon, and the field is boron. The concentration of the boron is 115 per centimeter cube. Wafer orientation is this much 001. And if you want to make a STI formation, this is a formation two transistors in a wafer, so that you can separate P and N, and where you can deposit the material oxide so that it is isolated between the two. And you can simply use deposit, and what you're going to deposit, you have to choose the material, what kind of deposition you want to try. So there are types of deposition. There's anisotropic, isotropic. I will explain what exactly these are, and these are the rates at which and the time for which they are going to get deposited. And so everybody knows that there is a procedure called implants. Basically dope the material so that it has some VT. So these are the VT and well implant commands, and you know that there has to be some mask so that the implant only goes into the area where it is needed. So basically the channel. Otherwise we don't need the implant. So we have to select a mask exactly like a process we do in the lab, and then we have to implant the boron with some energy and tilt. What I'm saying, a higher energy implant is going to get deeper into the substrate. If the energy is low, it is going to stay shallow. So if I just point it out that this boron, which is having the energy of 10 and tilt of 0, it is going to stay very close to the silicon surface, and it's going to be the implant for the VT. And this 250 is having a very high energy, and it's going to create a well implant basically. And when I said you have to shake the wafer, so basically you have to provide the temperature so that the dopants can get activated. And this is a simple command: diffuse, and the time for which you are diffuse all those species that you have doped, and the temperature you provide. So this is just a section where you can see how the simple words can do the job what you are thinking. Okay, so this is a picture that I want to show, and in this case you already know that there are some halo implants. and there are some source drain extension implants. So these are the source drain extension where my pointers are, and the shaded region is the halo implants. So already know that we have an implant command, we can select the boron, we can select the dose of the boron and the energy of the boron and the tilt. So when I say the tilt, it's actually tilted with respect to vertical direction. So if my tilt is 0, if my tilt is 30 degree, that means it is tilted from vertical direction as a 30-degree angle. And if the rotation is 0, that means it is assumed disk and it is sitting, and your angle of the implant is like this, like arrows. Now you have doped here at this point, but how do you dope here? From that angle. So what you do, you rotate the wafer, and as you rotate the wafer, this point gets into the picture, and you will have the same kind of source drain extension, or the doping profile you want. So tilt and rotation is actually the same way that you do in the wafer. You provide the commands and you can have a specific location where you want to dope the species for different exercises for halo and source drain extensions. Yeah, so professor was saying that the meshing was important, and this is the picture that can explain, I think, a little better. So when we say meshing, these are the points in the space where these all semiconductor equation plus the physics that you want to check is going to get applied and get solved. So as you already know that the conduction happens mostly towards the surface, and the channel is formed mostly more closer to the surface, not into the deep bulk. That's why the boxes or the mesh points here is the maximum, because we want it to be very dense so that it can have a very high accuracy. Of course, we are not solving anything. This is the spacer, and we are not solving our current equation in the spacer. That's why spacing or the mesh points are coarse, less basically. And you see this brown just above the below, just above the blue is the gate oxide. And of course, the gate oxide plays a very important role into the VT. That's why I have to keep a very high mesh in the gate oxide as well. So this is the way you can select and you can save the simulation time as well. So what you want to do, you want to have an accuracy, but you don't want to make the simulation go too long. So you have to select the region where you want to keep the meshing very fine and where you want to keep the meshing very coarse, so that your time doesn't go huge in terms of simulation time I'm talking. And this, don't worry about these commands, these are easy commands, and I will not talk about this at this point, but I will, when I do a live demo, then I will talk about it. So it's just the strategy how you can define your mesh. Now, as we have seen the generation of the device, I would like to show you exactly how you can generate a device in the simulator in the live session. So and I'm gonna do it right now. So few things I want to just believe me that how it's gonna be done, but I will show you the information, and the information is already there in the PPT how you gonna use it. But right now I'm going to show you how you can create a device. So don't worry about these commands. These are all explained in the later slides, and I will show you what exactly these are. But I'm just opening it so that you can see the device in the form that I wanted to show. So right now the simulator is opening. Okay. So I will show you the
Raghuram,
device. Yes,
before we
yes.
go to the device, so do you have any ideas that how they will be installing these things or license?
So licenses are already installed in MCL, And the way they can access is, it's already in the PPT. I will show them how to run the simulation, how to access the TCAD.
Okay, okay, fine.
Since I just finished the S process, so I just wanted to have them a picture
Right,
of mental picture so
right.
that they can see. So if I just go to, okay, why it is not visible? There is some issue. So right now I'm just going to one of my folders and try to access a device that I have already simulated so that you can see how does this device looks like. Sorry about the previous one, there was some issue and the device was not visible. I think this should be visible now. Yeah. Yeah. So I'm showing you a MOSFET, and I'm gonna zoom it in a little bit so that you can see the layers that has been there. It is somewhat slow because of the VPN. Okay. So if I just select the materials that has been there, these are the list of the materials that has been used in the device creation, and I can just deselect all and select one by one so that you will know where all or where are all these things. So if I just select my silicon, so you will know where all the silicons are. So you see that this is silicon, and this box, you just click the box and you can see the silicon coming up. Now, of course, this is the net active. So if I just check my doping concentration in the fields, then you see the boron active. If I just select this one, you see this is the boron active concentration. So because this is the source drains are boron planted, you can see the boron concentration, which is like 3.9 E21. It is the highest in the source drain, but lower in the channel. And if I just select the arsenic, you can see this is the concentration is somewhat in the channel. So like this, you can select the doping concentrations, or you can select the fields. And if you want to see the, okay, so let me just deselect it. It's a bit slow, somewhat slow. If I just go back to my net active concentration, now if I just select my oxide, you see that the oxide is present as a spacer. And if I select my interfacial oxide, that should be the oxide right above the channel. It's selecting something else because of the slow internet. Yeah, okay. So you see this very thin layer of green thing. This is the channel oxide. And if I select HFO2, it is deposited right above it. So this is the HFO2 SiO2 combination of the gate oxide. When we were talking about meshing, these were the thing I was talking about. Our professor has already mentioned that these are the points. So you see, the points that are dense is actually in the active area of the transistor. And these are important because you're going to solve a lot of equations that requires very high accuracy, so that your IV doesn't look like something else other than IV. So that you need to have these mesh points very much high in the active area, and you can relax in the points elsewhere. So this is how your structure looks like. And if I just show you the contact, those are important things. So let me just deselect this one. Okay, so let me show you the contacts. Okay, so it is just clicking somewhere else. So if I just select drain, let me just turn off the mesh so it is off. Let me just wait, let it come. What just happened? Okay. Please bear with me. This is going slow. Okay. I have to zoom it a little bit so that you can see. So you see this pink region? Do you see this pink region? If it is visible in the screen?
Yes, sir.
Uh, yeah. So this is the drain contact I have just selected. You can see that I have selected the drain contact and it is visible at this point. So in the simulation regime, we just provide the contact in two ways. One is the line contact, which is the 2D way of doing it. And if I just select the source, you will see a contact running on this side. And yeah, the pink line you see, this is the contact line. And similarly, if I just select the substrate, at the bottom of this whole thing, you will see the substrate contact. And if I just select the gate, you will see the gate contact on the top. So I have to zoom out a little bit so that you can the gate contact. So here, these are the points where you will apply the voltage and see your device working. So you see this pink thing, this is the gate, and the thing that you see as a rectangle or log, this is the gate metal I have deposited right on top of the oxide. So this is how you can provide gate, source, and drain and substrate. So let me just select the substrate as well so that you can see the pink line for the substrate as well. Okay. Gone very slow. Okay, fine. I mean, it is there. Believe me, it is there. I will show you the projects and I will give you the example projects, and you can see. So yeah, you can see that there's the pink line coming up, and this is the pink line for the substrate contact. So this is how you can, this is how the picture looks like when you create a device. Now it's time to provide some voltage and some temperature, define some physics so that we can actually get an IV curve. That is the goal of having the device.
So
Okay.
let's hold. So Ravi, let's see
Yeah.
any questions are there from
Yes.
here. So anyone is having
I
any
have a
question?
question.
Yeah,
Yeah.
please.
So is it a 2D or 3D structure, or is it the actual structure?
Yeah, this is the 2D structure. So you know that the MOSFET has a length and a width, right?
Yeah.
So the structure is created in the length direction, and if you want to have a width, you can have a width in the z direction, in this direction. But since the width is actually excess of symmetry, if you just take a slice in any width frame, you can have this kind of device. So whatever current you will get out of this, this is basically a 2D structure. You have to say that what is the width of a device. By default, the width of a device is assumed to be 1 micron in all the simulation. So whatever current you will get out of here, that will be per micron. So if I just get some current, the unit for those, the value that you get will be some per micron. Per micron is per width, and width is 1 micron assumed by default. So this is the 2D structure. You can have 3D as well. You want to see the 3D, I can show you the 3D as well. But let me just let me just, 3D one being loaded while I go and tell you the device. So I'm let it just open. Okay, so this is now being loaded, and let me go back and tell you how you can actually characterize your device. So as device, Centauros device, where you're going to apply some voltage in the device, where you have provided the contacts, the pink lines that I've shown in the 2D structure of MOSFET. There you can actually define some physics. You can define the temperature. You can define the voltage ramp conditions. You can select the fields you want to show. You want to check during and after the simulations. Those all will be done in S device. And what exactly is S device? It's a multi-dimensional device simulator capable of simulating electrical, thermal, and optical characteristics of silicon-based and compound semiconductor devices. So this is just a definition out of the manual, so that I don't digress from the issue. I mean, from the point. So how does that S device command file look like? And it's just a very simple setup, and it's not sequential, because command file is just a setup where you are putting the device out of your S process and defining some physics, putting some voltage, and solving some equations. So the four important section. One is the input and output file section. Of course, the input should be the device, which will be in format of TDR, and this will be the output of S process or SD, where you generate a device. The parameter file is the file where you keep all those model and material parameters that are going to get used in the device simulation. And then of course you will have a plot file where you will have a XY data for your IV and CV that will be generated after the device simulation. And then you will have a current plot where you will see the fields, how the electric field has been developed when you have, let's say, applied the drain volt of 1.5 volt. And then you will have an output file. You need to define some electrodes, of course, and you need to define the initial voltages and the resistance of those, how the resistance looks like when you have a contact. So initially you define your voltages to be 0, and then you ramp it, and you solve all those equations every time when you ramp the voltage, so that the field, the doping concentration, that electron density are exactly accurate as it is happening in the real device. Yeah, this is the most important section, the physics section. And the physics section is the one that allows you to check different physics. Now, a typical physics section will have some models. So these are the name of the models, and don't worry about these. Just let me just give you a simple one. So if I just select my material as silicon, and I want to check, I want to put a mobility model. So you already know that the mobility has different definition based upon what exactly the voltage you apply, and what are the simulation you're going to do. Now, based upon the experiment, you need to select the mobility models that are available. And these PHU mob, this high field saturation, that E normal, these are the keywords. These are the keywords to select some particular models, basically some particular equations that are available in the Centaurus. So this is just a picture how you can select the keywords and put where you want to solve the physics. Now the plot section. So basically plot section is the one where you want to see what happened to all these quantities right after the characterization. So you can check the electric field, you can check the electron and hole density, you can check your mobilities, you can check the recombination rates, where it is happening max and where it is happening low. So these are the plot fields that you can set up and you can check right after the simulation. Just hold on. Yeah, sorry. So this is the math section, and the math section is allowing you to have some numerical, knobs so that you can control your convergence when you're solving a lot of equations in 2 dimensions, 3 dimensions. You need to have some controls, and so that your solution converges without getting failed. So these are the knobs, and these are basically fixed when you pick a let's say an example project from the library. These are the things already fixed. But if your solution is not converging, you can try changing one of it, but you need to read what exactly these control points are in the simulator. So this is basically the control to keep the math in a manner so that your solution converges. That's it. And then you have a solve section, and this particular section is the one where you are actually applying the voltage, basically ramping the voltage to a certain point, and every time you ramp it, what are the equation you're going to solve? You put the equation by its keyword. So if you want to solve let's say Poisson equation, you put Poisson and you say coupled iterations, and these are the words, just the keywords. If you just select the keyword and check it in the manual, you will see what exactly is its meaning. So you solve first for the equilibrium, because you need to know what is the status of the device when it is in equilibrium. And when you ramp the voltage, how the equilibrium going to change. So you need to have an equilibrium solution first, and then you are going to change the voltages. So this is how you can actually change your drain voltage. So you say, okay, my goal is to ramp the drain voltage from some VD-lin, and my VD-lin in the experiment was 50 millivolt in the command file somewhere up, but just showing you how you can put a equilibrium setup and then you can ramp your voltage. And here the order is important, because you can't just have a non-equilibrium solution first and equilibrium later. You need to keep your solve section in order. Yeah, this was the parameter file I was talking about, and all for all the materials, whatever models are available, basically whatever the equations are already implemented in the Centaurus, for all those parameters, this parameter section is going to access all those and give as an input for the S device where you're characterizing the device. So this is a simple parameter file section. I will show you how does it look like. And this is the slide, not important right now, but when I show you, this slide will be helpful. This organizer, I will show you what exactly is this, but just a brief that you wanna do. Let's say you have a device and you want to check how does the IV looks like if I am changing my channel length. So you can have a device of different channel length. So let's say this particular value of L gate is basically the length of the channel, and you can have 60 nanometer, you can have 20 nanometer, you can have 100 nanometer, you can have 180 nanometer, and all these horizontal lines are going to produce different devices based upon the channel length you provide. And then for every channel length device, you can check your IV and you can compare the IV. How does it changing if I am just changing the channel length? So this is just a project organizer, the CentOS workbench, so that you can have a device generation and you can have your characterization all in order and synced with the corresponding experiment. I will show you the organizer.
Okay, just
Yeah.
to add over here, you guys can see this everything in this like in the software is in the scale of micron. See, he is showing this
Yeah.
L gate. It is in micron.
Yeah.
So normally this software, so it's conducts all calculations or all inputs in micron order. And
Yeah.
also keep remembering that, let's see, this fast device is what he is showing, uh, the FATE MOSFET. This FATE also it you should be very careful when you are designing the thickness of the silicon. See, this metal thickness is somewhat in nanometer, and the normally we see this on silicon wafer thickness is somewhat starting from 300 micron to 550 micron. Like 4-inch wafer, if you take, so that is the 550 micron, or like if you take a 2-inch wafer, that is 300 micron. So silicon thickness, you need to be very careful. Then when you are using the metal, that we normally use 100 nanometer or 50 nanometer scale. So when you are putting some of these length scale or the thickness scale, so need to be very careful, because those can changes your device performance or device output, or the structure of the device can be entirely changed. So those who are going to start newly this software, so keep remember this part of this important part of the software actually.
Yes.
Okay, so if there is any question from others, we can discuss. Okay,
Sir,
so
I have a doubt.
please go ahead. Yeah.
Yeah.
In one of the slides before, there was a statement quasi-stationary. So
Yeah.
I did not understand what the quasi-stationary means. Yes, yeah.
Okay. So by meaning a quasi-stationary solution, that means you're going to so it's not exactly transient. It's in the steps. So assume that you have a device, and you know the status of the fields, the electron density, the free electron density, and the bands, the potential. You know everything when it is in equilibrium. Okay. Now if you ramp your voltage, you cannot just have a voltage applied directly of, let's say, 1.5 volt at drain. If you apply 1.5 volt, and if you want to have the status change from equilibrium to 1.5, it's not going to get conversed, because you need to solve some fields, you need to solve some Poisson equation. So all those things is not going to get changed directly. So what you need to do, you need to ramp your voltages in steps. So you see the max step, you see the initial step. This particular quasi-stationary step of ramping the drain voltage in a ramp-like manner, in a step-like manner, is the job of the quasi-stationary command. Are you getting?
Okay, sir, I got it.
So for example, you remember that when we are doing the CV measurements, we first we first fix the DC voltage at a particular step. Then we apply the AC and measure the capacitance of a particular point. Then we go to the next step, increase the DC voltage steps, and then again we apply the AC. Then we find this capacitance at the particular DC voltage. So that step by step you increase and then find the capacitance value. So here also similar way you can do it. You can actually change the your voltage sweep in a particular step. Then you can measure your current after each step actually. So like at each step you are fixing your parameters or whatever you need, and see the output what you are getting actually. So this is a similar way what we see in the CV curve also. We'll get more detail when the transistor will be started.
So this is just the way we do in the experiment. We raise the terminal voltage slow, step by step, like in some step, like 50 millivolts of steps, or like 100 millivolt steps. So this is the similar manner, because every time you change the voltage, things inside the device, like field, the energy bands, the Fermi level, everything is going to get changed. And every time it is changing, the simulator has to know what is affecting and how much it is getting affected. That's why you need to ramp the voltages in the steps. That's it, I think.
Okay, if there are
Uh,
any other question in this?
Hello, sir.
Yeah.
Like if we want to measure the voltage, we want to simulate the voltage from negative to positive, like -1 to 1. So
mhm.
first we define for equilibrium 0 0 volt. We perform the Poisson equation for equilibrium condition.
Mhm.
Then we will ramp to +1, and then we will again go back to 0 and then -1 or something else.
You can define like that, of course.
Okay, sir.
Yeah, you can define. You're telling that for from positive to negative voltage, if you're ramping. So even for that, you need to have your equilibrium solution ready so that the simulator knows how does it look like when it is in equilibrium, and then it can change the voltage into the in either direction, positive or negative.
Okay, sir. And one more thing, sir, is this language is case sensitive or not?
Yeah, it is case sensitive. It is
Uh,
case sensitive. So you can't just put a small L here. It is case sensitive.
and also, is there any limit on the meshing, like how much we can reduce it?
Um, there is no limit. It's the sense you need to have. Let's say if you're doing a quantum something related to quantum potential. So do you think that solving a quantum potential will be okay if my mesh is in microns? I don't think so, right? It has to be in nanometer or angstrom scale, right? So
Yes, sir. Yes.
depends upon your experiment. You need to define your mesh spacing.
Like we are doing electrostatic, then how much we can reduce?
And that's also based upon the length where you're scaling. So assume that your channel length is just 20 nanometers, and
Yes,
if you
sir.
have just 2 points between the channel, it's not going to help. It's not going to give you a good solution. So at least you should have 30 to 20 or 30 points, at least 10 points, so that simulator can solve the potential from source to the potential at the drain, because those potentials are different and the things are going to be different in terms of band, in terms of energies. So simulator needs to have some points where it can actually get a converging solution for all those quantities. So it always depends upon what you're simulating, what is your dimension, and whether you can get a good solution out of it. That's how you need to define your machine.
So
Okay, sir.
Kunal, to answer your questions, which is what is the minimum length you can take? So the minimum length is your atomic length, right? So you can build one atomic transistor, right? So that you cannot go beyond that, like lesser than that. So of course you can so if you are going for the 20 20 nanometer thick like length of channel. So if you want a good and accurate solution, you can have a 40 points, right? So like half nanometer of each. So that would be like a good estimation or good understanding that what you are getting. Of course, you can do lesser than that also. You can go beyond that, like in the software can hold it. But for the reasonable values is like you can have atomic length and see that how your result is getting converges. So it's completely depends on that how accurate result you want actually. So if you want a completely 100% accurate, so you need to make a mesh very thin or very small size, so that you are getting close to 100%, but you will never get 100%, because that is the error also will be there. And also there is another problem is there, because let's say you go to the very small size thin mesh. So your simulation might go for the 2 to 3 years, that you cannot complete your PhD within the time frame. So it depends on that how much you want and what is the time frame you want. So all depends on the timing and some percentage of the accuracy, and then we can move actually with that results. And the paper or like a journal also, they are acceptable, that you have some good percentage of the results that you are getting, and that can be acceptable by the journal, or if you are filing the patent also. That's a reasonable percentage they want. So we don't need to be go for extremely um, thin or very small, or the other way around. We need to go to the extremely high, so that the accuracy of the results is not so good. Okay, so I think if you do the hands-on, when you start your research, or when you'll be doing your work with this software, then you will have a more understanding that how much you required actually.
Okay, sir. And also one more thing, like the mesh size is depend on the minimum step and maximum step also in quasi stationary.
They are related. They are related. Of course, if you put a max step very close to min step, the ramp time will go high. That's it.
Will it depend on mesh size
Of
also?
course, yeah, of course. So if
Okay,
the mesh is very, so let me just go back and show you. Okay, so do you see the mesh here?
yes, sir.
Yeah, okay. So every time, so assume that this is the contact, or there is some contact here, and you know that this metal is having the same potential throughout. There's no change in the potential. That's why the mesh is coarse. But because the silicon is having a different energies based upon the potential applied at the gate and the source and the drain, there you need to have a very fine mesh. So of course it is going to depend upon what kind of mesh and what kind of solution you want. And if you have a very fine mesh and if you have a max step with which you are ramping your voltage, the drain voltage or gate voltage, if it is very small, it's going to take a longer time. That's it.
Okay, sir. And if we don't provide minimum and max step, the simulator will take by its own value.
No. It will not take. Solve section you need to always define. And there are
Okay.
examples available. You can use, there are basic examples available for IV, CV of MOSFETs of different channel lengths. So you can take those examples and you can check. I will show you where are those examples available and you can take those examples. Okay, should I proceed now?
Kunal, you have any question?
No, sir. Okay. Thank you, sir.
Okay.
Any others have any questions? Okay, if there is no question, please go ahead here.
Okay. So I mentioned that this SWB, the fourth tool in the picture, let me go back and show you. So I told you about these four tools: process, device, visualization. And so visualization is the tool that I was showing, where I was showing this one. This is the S visual. You can see in the left top corner, you can see the visual written, CentOS visual. So short form is S visual. And don't worry about the commands. The commands are already listed in the PPT, and you will have this PPT by the end of the presentation. Okay. So this is just the organizer where you can organize your experiment very nicely, and you can check how the how your, if you change it. Let's say in this experiment it is changing the channel length. So you can check for this channel length. If I just travel horizontally, I will have an IV based stored with the data somewhere with this one. And if I just check the IV of 180 nanometer, so these are in microns as professor pointed out. And this, the IV of this you can check here. So you see this is S device, the characterization part, this is the generation part, and this is the visualization part. I will show you how you can handle all this SWB, and you can check the, this is just the way you can check the status of your simulation. I will show you when I will run the simulation in front of you. And this is how you can log in and get the TCAD accessed using MSL. So logging to the MSL server requires your username, which will be provided by the TAs or the RAs of the MSL lab. And then there is the IP of the machine. You put the IP here. So there is a mobile extern software. You go and Google the mobile extern software, you download it, and then you go for the SSH. You put the IP address here, you put your username here, go enter, and then the software will look like this. So let me just open a new session for you. So this session is already saved. If I just click, so you see the IP address and the username. So this is our machine. That's why it says test. If I just click it, double click it, I will have a terminal open for the device, and these are the folders available in that particular machine. So we have different users, Rashmi, Nilotpal, and you all guys will have your own names, and the projects will be all there, all inside your directory, whatever you want to do. Now if I just show you how you can how you can see where are the example projects and you can copy and paste in your folder, and how you can just run a single simulation, because that's the goal of this whole tutorial first, so that you can check your knowledge. So if I just type swb, these commands are already there. So if you just type swb, you see it says Centaurus Workbench, the name I mentioned as a tool, and it's going to open some version. So this is the version information. So it says that 2017, but that means this version of the Centaurus was is actually old. It's like 4 years or 4 years old. There are other options available, and you always ask your RAs to have a latest version installed, and latest should be the S release, which is 2021. Now, as you enter the command, you see there is it asks for you to choose a directory. So select your home directory and say OK. And it says the CentOS Workbench is opening. It tells you about the version. Close this. Yeah, it is opening. Give it a second. So you see there is a window. This is the GUI, and you see projects, edit, scheduler, view, scenario. Let me show you how you can get a simple example project you can run, and you can see the device and the IV. So this is the home folder. If you can just see, this is the home folder, and if you go down, you will see something like a library. So if I just extend this part, you will see something like an application library. And in this application library, you will see projects of different devices. So if I just select CMOS, let's say, I will have these projects. So these are actually the project that are already there as an example. So if I just, let's say, as I just take this one, or let's say if I just say CMOS processing, right click on it, you will see copy option, copy it, go back to your home directory or go back to your folder. So let's say this is my folder. It's let's say this is my folder, and I want to create a new directory. Right click on it. It says folder, it says new folder, make a new folder. So let me say it's the TCAD. And since I've copied that project of CMOS processing, I select the directory. Okay, let it happen. Okay, I select the directory. It says paste. So paste it here. So it says that copying from application library to the TK directory. So you see that CMOS processing example project is now in your directory. And please always copy and paste it in your directory. Don't run anything in the example directory, because that's the reference that anybody can take and run. If you run it there, you might mess up the example library. So you see one says dash process, the other says as device, and you see if you just look at dash process, you see that some simulation to n, simulation to p. These are some variables. I will show you what exactly these are. And you see L gate, it's 20, 30, 20, 30. These are the 20 nanometer, 30 nanometer. And there are some steps or segregation between the processing steps that you use to create a device. It is um, um, segregated from step to step. And then you have as device, where you apply the VDD, basically the supply voltage for saturation current and supply voltage for drain, the linear current, and then you simulate the IV. You can you can check the result in S visual. You can check the IDVD saturation here, and you can check the IDVD here. So this particular project, if I just copy CMOS processing, you can see everything is here. You can change the things. You can check your IV, you can check the IDVD, you can check the CV as well. So right now I'm just going to show you how you can actually just create a device. So as I told you that there is a command file. So if you just select the tool, say edit input, it says commands. So if you just open the command, oh, it is coming. It's because of the, okay. So yeah, here it is. So you see some bizarre, codes here. Don't worry about it. There are some basic settings for the simulator, so don't touch that. Just look at the thing that means something to you. And let's start saying that, okay, the region is silicon, that there is substrate, the name of the silicon is, we are defining a substrate, and we are defining some concentration, field, boron. I think this is the cut that I've taken to show you in the PPT. And then you have a dopant field. So it says there is a in all the example projects there is a document, and there is always some notes what exactly is happening anywhere. So you see this command file will create a device, and let me just run in front of you. So how do you run it? So let me just give you a simple brief. You see these horizontal lines, these are the number of experiments. So if I just select this one, this will be one experiment. Okay, this will be one experiment. And to get my device, I need to run all the nodes. So if I select all those with control, and it says there's a running guy, it says run selected nodes. If I just click it, it says run project. It asks for the permission. Just say okay. And now you see the colors. Okay, just this is the log creating. Don't worry about it. You see the colors. So blue says it's running, and the later parts, later segregation of the whole CMOS fabrication is in pending or queued mode. So let it run, and in the meantime, let me show you the 3D transistor. So I think for today's class, let me just focus up till S process, and the next tutorial I'll be able to show you the characterization part and how you can check the IV and fields. I think is this okay? Right, Professor?
I think we need to stop in 2-3 minutes because
Yes.
there is instruction that we need to stop at least 10
Yeah.
minutes, 5 to 10 minutes before the class.
Okay, sir. So just give me 1 minute.
Yeah.
So as I opened the 3D structure, somebody pointed out, can we have a 3D structure? So summarizing the things that up till this point we have seen, using S process we can generate the device, using S device we can characterize the device. But right now somewhat like a hands-on is getting started, and I just showed you how you can run a simulation, and just showing you what exactly a 3D device looks like. So if I just select this one, so you see this is the 3D transistor. Let's look at it in the next session, because if you have some questions, this will take a couple of minutes.
Okay,
right
so
now,
let us see that if there is any question at this stage from anyone, because you can see this 20 nanometer transistor taking how long it is taking time basically to run the simulation.
And so, it's a 2D simulation.
Yes. Yeah, so that itself is taking time. So like if you have a larger mesh, you will have you can imagine how long it takes. So normally, if you are going to take such a standard simulation, it takes like a 1 week, 2 weeks, sometimes about a month. So it takes time to simulate the entire devices. There was a question from like several times that how long it takes. So it takes a time. So if you have any question at this stage, we can discuss. The rest part we can conduct in the coming Friday.
Sir?
Yeah, please continue.
Yes.
Yeah, so as all devices are in 3D we have in actual, so why we are running these 2D simulations?
Yeah, so
Means if
as he
I
yes, as he mentioned that, see this. Of course, you can go to the 3D part. See here, you can see the construct the 3D part. But ultimately, the 3D part is the g-axis. Like you are increasing the g-axis. If you have already like if you already have the x-axis or xy axis, then you can of course always have a g-axis on like on set. You are ready with the g-axis. See this right side panel here showing the g-axis that you can
Yes.
form actually g-axis by from the 2D simulation also. It's not the problem actually. It just depends on that how you want to do construct your devices. Robbie, you want to
Also,
add
just
something?
yes, sir. Yes, sir. So we already know with the simple logic that if we have a symmetry and if we just solve one, and then we can predict how it does it look like in the other direction. So as you already know that the width of a device, width of a MOS transistor is actually symmetrical in the direction of its width. So if you just take a slice and if you just check the how much current is coming from one slice, and then you can multiply your current with the number of slides, and then you can get the actual value of the current coming out of a 3D device. So you don't really need to simulate the 3D device unless it is not symmetrical. If it is symmetrical, you just take a slice, you do the simulation, you get the measurement out, and then you can multiply with the width and you can get your IV for a 3D device. So because it's not always important to replicate everything what is happening in the experiment in the lab, it's important to get the information out in an optimized manner within a calculated time, because you can always run 3D simulation, but it's the matter of time. So time is the most expensive thing here rather than having a anything. It's the time. So you want to get your simulation done in a very short time and get your accurate result. So and we have tested that if we have a 2D device versus 3D device, and the current what I'm getting out of 2D device, and if I multiply by the width, it is exactly same as the 3D device. So you don't need to simulate the 3D device unless it is not symmetric. Are you getting my point?
sir,
Whosoever.
but
Uh-huh.
sir, in like we are using that as process in which we are kind of virtually fabricating that device, right?
Mm-hmm.
So if we are fabricating that device in 3D manner, then there will be more strain, stress kind of things in that device, right?
Yeah,
So
true.
will those parameter not affect that characteristic?
Yeah, so okay. So if your simulation, if your experiment has some variable that is not symmetric in the direction of the width, let's say if it is not symmetric, let's say your strain, you're trying to capture the effect of strain, it is not symmetric, then in that case you need to simulate, you can't simulate 2D device, then you need to simulate the 3D device. And that's how I have a picture. So if I just select this picture and show you. Okay, so you said strain. So let me show you. Okay, so this takes time. So because the structure is very big. So if I just remove the tungsten, HFO2, nitride, let it happen first. Okay, the low K. Okay, where's the low K? Nitride. What is this? Okay. So if you see this device that I just selected, let me zoom it a bit. There's the zoom button. Why it's not active in this case? So in this simulation, so you see the blue things. Can you see these blue things?
Yes, sir.
Okay. So these blue things are the source drain, and it is having the germanium content in it, basically with silicon. So this is silicon germanium, and this gives some strain in the channel. so that the mobility of the PMOS transistors or P substrate transistor goes very high. So in that scenario, you need to have this source drain because it is not symmetrical in this direction. Do you see it? Because it's going to get some strain out of the 3D geometry, and geometry plays role in the amount of stress or strain getting in the channel. In that scenario, you need to have the 3D device and you need to run the 3D simulation. But here in this case, it's a long channel MOSFET, and there is no stress and strain coming out of source and drain. If it is there, 2D also can handle. But since the MOSFET is symmetrical around, is symmetrical in the direction of width, you can actually take a cut and you can still simulate and you can get the accurate result. But in this case, in the so this is a modern transistor where you need to have this geometry because the structure has changed, the architecture is changed, so you can't actually simulate a 2D out of it. You can have some prediction if you take a cut and simulate, but the accurate result needs to have a 3D simulation done. So it depends upon what exactly you are looking for in your experiment. If it is requires the 3D simulation, you need to do the 3D simulation. If it is having some symmetry and you can get rid of the 3D simulation, you better get rid of, because 2D takes 1/10 almost of the time, and 3D takes humongous amount of time. Does that answer my question? Answer your question?
Yeah. Thank you, sir.
Okay. Any other?
So is there any other questions? Okay, if no, you
Sir,
can check this. Yeah, please go ahead.
Sir, in this spreadsheet, you selected only the first row. Can we select different elements from the spreadsheet?
Which rows you're saying?
In the workbench.
Okay, okay. If I go to workbench, yes.
You selected only the first row. Can we select any other elements? Or
Yeah, okay.
like from other rows also?
From other rows. So let's say if I select this one. So if I select this one and try to run, you're saying this one?
Multiple, like
Okay.
from multiple rows.
Yeah, you can select multiple rows. See, I just selected, and if you can launch, but this will not run parallel. This will run right after when these are done. So you will see that this is going to be in pending mode or queued. See, this is now in the pending mode. You can select, no problem.
No, I am asking that we can select from different rows, like from first column we select the second element, and from second column we select the third element, like this.
No. So you can select, no problem, and you can run. So let's say if you select this one and you try to run this one, both this one.
Yes, sir. Yes, sir.
Like this. So in this experiment, these rows are designed as a single experiment. So if you run this one, it's not going to give you a device if you run this one.
Okay, sir.
So these are the tree. These are the series of commands happening in a row. So if you want to get a channel device which is having 30 nanometer of channel length, you need to run this row only, the whole row. You cannot mix with the upper row or the lower row. Rows are the experiments. Columns are not. Columns are the different values of a particular thing, but single device is going to get by running the particular row.
Okay,
So
sir.
for
Thank
example, if you have the one you just finished now capacitor, let's say you have a thickness of a capacitor or the oxide thickness of 10 nanometer. Now you can use, let's say, the maximum 5 volt or 3 volt to 5 volt you can use maximum voltage, right? Now if you are going to use that 30 volt, which always used for, let's say, 100 nanometer thick oxide, if you use 30 volt, then the devices or the capacitor will automatically damage, right? So that is not going to, you are not going to get any results from there. So it's like if you have the fast row that is designed for this particular devices, and if you wanted to use the fast row on the second devices, then on the second devices what is written the gate voltages or a gate current, then the result, you will get some results, of course, but that will mislead you actually. For example, if you, let's say you have the 100 nanometer oxide, thick oxide on capacitor, and if you are applying, let's say, zero point 0.1 volt, you are not going to get anything actually, because there is no leakage from there, because you are, if you are trying to measure the leakage current, if there is no leakage, there is nothing you can get from there. So you need to have close to the parameters, or like which parameter will be useful to implement or to get some results from the devices. So the right set of parameter is very important. Even it is not right, it should be close to the what device is required. So you may have some better idea or some guess before implementing or before using the devices, or like before giving an input to the devices. It's a similar like experiments what we do in the lab, that we cannot use, let's say, 1000 volt, what you are using for the bulb opening 1000 volt on a capacitor. Of course, you can have a larger capacitor and use the voltage. Same over here, you can have a particular devices which is, let's see, I get, you can see 20 nanometer, and you can see the 30 nanometer. So 20 nanometer have a different set of values, 30 nanometer will have a different set of values. So that you need to have a like ideas that how much, which parameters will be useful for this, which parameter will be useful for the larger devices or larger gate or larger devices, whichever you feel that it would be useful. It depends on the device to device, right?
Right, sir.
Okay, thank you,
So
sir.
I think your simulation is still running.
Yeah. I think, sir, in the next tutorial, I'll be able to start from where I'm just leaving. It's like I will show them what and how the different channel and devices are created, and they can see the difference in the channel length. And then in the hands-on, in the next class, in the hands-on, I can show the IVs and how does the IV look like. Then these questions about the simulator and the setup will be more clear for them.
Right. Okay, so if you have other questions, so you can directly reach to me or Rabi.
Yeah.
Of course, we will have the next week again. Not next week. Next Friday, coming Friday, we'll have continue from here where we are stopping now, and then you'll be ready for with this TCAD, and we'll start this transistor in the next after your mid-sem exam actually. Okay. Shall we stop over here?
Okay.
So I'm stopping the recording.
Okay.
So other can